Christoph Hoyle is Manager Technology Development for Spatial Light Modulators at Fraunhofer IPMS. And Christoph's topic today is manufacturing process challenges for MEMS-based holography SLM devices. Christoph, everything looks all set, ready to go. Everything looks great. You have 30 minutes total. So again, please aim for about 25 minutes speaking portion, and we have some time then for Q&A.
Perfect. Thanks, Mike. Actually, I was pretty happy to follow the panel discussion this morning, and it was showing that a couple of other companies have the same issues, the same problems as every day, as also our institute, Fraunhofer in Dresden, has. So
Yep.
I have asked basically by the organizers to talk a little bit about manufacturing challenges when processing MEMS-based SLM holography devices. That's somewhat difficult for Fraunhofer, since Fraunhofer is an R&D company or institution, but nevertheless, I guess I can show you a couple of examples from manufacturing in the upcoming 25 minutes. So I'll start with the motivation for real 3D imaging for various types of realities. Then I give you an overview about our micromirror arrays at Fraunhofer Institute for Photonic Microsystems. Then I go into future MMA displays for holography with some conceptual studies, development for proof of concepts. And then the focus will be then, of course, on the process challenges, followed by summary and outlook. So on the internet, you can find various types and pictures, nice pictures and animations for virtual reality, augmented reality, or a mixture of that. So you can use this as assistants in everyday life, for tool and machine interfaces here, for design and project studies and so on, also architectural studies, and that's pretty nice, but it's basically all fiction, so it's not available today, and if it's available, then it has a lot of problems I can show you. So basically all these systems are 2D stereoscopic systems, and no 3D animation is possible. So our focus, and that is also focus of the talk, is so-called real holography. And application scenarios would be, for example, holographic automotive head-up displays, HUDs. In that case, the information is displayed with correct spatial 3D placement. So not only on the windshield, but you can actually feel and see them in space at the right position where it really belongs to. You can, of course, for example, mark potential collisions, additional traffic lights that may be hidden. It gives you direction, guidance, other additional vehicle data, and assistance in everyday life. With this system, of course, other application scenarios are under consideration, such as structured illumination or active headlights, and so on. For real 3D holography, what is needed? So to display people, objects, and so on, classical stereo 3D is good, but it's limited. It has only a very low depth range that goes into probability of fatigue, and that's why widely the systems are not widely accepted yet. We think that computer-generated holography is much better suited, as it gives you an identical vision, a natural vision of experience. Key components for these CGAs are so-called spatial light modulators, SLMs. That's basically an arrangement of micromirror arrays, thousands or millions of them, that prospectively can surpass other SLM options, such as ribbon type, liquid crystal-based LCOS systems that are not fast enough. In our case, micromirror arrays are polarization independent, and crosstalk between pixels is widely avoided. So that gave us the ideas to apply for an EU Horizon 2020 project that has been granted last year. And focus is definitely the development of a phase modulating micromirror array for real holographic mixed reality display. So a lot of buzzwords in here. And we partnered up with our collaboration partner, Serial Technologies, also from Dresden here, who's basically responsible for the system and the technology. We have the part of the MEMS in here. And Solution is the CMOS design company of choice, OmniChip, the Adders Electronic. Then we have Sensio here for the packaging. XFAB is providing the CMOS backplane. And last but not least, Valeo is the automotive application in the end. So a nice partnership in here. We started about a year ago. 3 years are running, and we are basically in the midst of MEMS manufacturing, and I can show you the examples from that. First, I hope I can try now to start a movie in here. Hope you can see that. And
the world of mixed reality and 3D are finally emerging as players in the next generation of high-tech optical devices. You might think that that's not really news because 3D displays have been around for years. The truth is, many 3D products are actually only 2D images enhanced to create an illusion of real space. Problem is, this stereoscopic 3D effect, as it's called, can cause physiological side effects like eye fatigue, misjudgment, motion sickness, and problems with eye focus. Only holography can produce true 3D. The Real Holo project will enable real holographic displays by researching and developing an advanced micromirror-based spatial light modulator to create high-resolution and precision holograms. But what exactly is a hologram and what can they do for you? A properly generated hologram written into the light modulator, then correctly illuminated with a laser, creates the same light waves that a natural scene or object would reflect or generate to the human, thus creating the exact equivalent of a real object in space. Holographic 3D objects are essentially faithful reproductions of all visual object properties with full motion and depth of field, just without the sensation of physical touch. In Real Holo, partners will use microscopic mirror arrays to alter and control the light to display the holograms. Let's get back to how these holograms can benefit you. Imagine a head-up display that not just shows a flat image at a fixed distance from the windshield of the vehicle, but actually projects objects like navigational icons and pedestrian warnings at any distance and properly spaced outside the vehicle. This mixed reality environment has no limits when it comes to safety and security, or entertainment and information. 3D that works for everyone without negative effects is around the corner, and the Real Holo project is pushing it to reality.
Okay, how do I get back? Here we go. So, short journey into real holography, and I'm going to continue and show you what we provide for that in the MEMS business. So basically, we are operating a 200mm clean room in Dresden that is state-of-the-art, it's fully integrated and CMOS compatible. So this is used for R&D and pilot fabrication, low volume. We run it in 24/5 operation mode, 3 shifts. Significant amount of people are working in here in operations, engineering, and maintenance. I'm going to talk about more about our litho applications in here. 1,000 wafer starts per month. It's CMOS compatible, class 10 certified, and it's operating in an MES system, a manufacturing execution system, state of the art, that traces and documents whatever we do. So the flagship of our clean room is basically the new 248 DPV litho cluster, a state-of-the-art tool, of course, for classical DRAM manufacturers, but not in the MEMS business. So with this tool, we are probably entering the nano era for true MEMS. The tool, of course, a couple of features in here. Besides resolution and overlay accuracy, what is really good for MEMS manufacturing is the larger exposure field, comprising much higher area than the currently available eyeline lithography. Well, this tool has been installed about a year ago. Integration is ongoing. Process development is rather challenging in here in the classical MEMS world. The tool has only been possible to set up with a significant amount of money by the European and the German governments within the umbrella Forschungsfabrik Mikroelektronik. So a couple of devices we are manufacturing and providing in our business unit. The micromirror arrays by IPMS are a couple of device examples in here. We use it for various applications, for example, as programmable mask. You see here 1 million of tilt mirrors, 16 micron pitch and 2 kilohertz operating mode. It can be used for direct imaging, a line of 8,000 individual pixels. Already 2.2 million tilt mirrors, much faster in speed to 1 megahertz operation, and a couple of other applications such as microscopy or adaptive optics in tilt mirror operation or in piston mirror operations. This is just an example. We have more devices in here. Some of them are confidential. We cannot talk, but it's really nice to work on that. Most of these devices are, of course, driven by speed and the correct wavelengths. You need a couple of key competencies in manufacturing these devices. Some aspects of MMA development. Of course, you start with the CMOS design and simulation, the backplane that is necessary. In here, we have some in-house capabilities for larger CMOS devices, up to 5 micron. For smaller nodes, of course, we couple up with external partners like foundries. We have know-how in the MEMS design and simulations, finite element simulation, analytical simulation. Our core competence is definitely the MEMS processing itself. We are to generate these devices, we use surface micromachining techniques such as release technologies, gas phase etching, HF, xenon defluoride. You know all of these things to generate freestanding objects in here. All of these processes are CMOS compatible. We use the standard monolithic integration approach. Chip packaging is necessary. We have know-how in the characterization of these devices on CMOS, on MEMS level, wafer level, and chip. Electrical, optical, and mechanical characterization is available in-house in order, for example, white light interferometry to show these individual mirrors. Last not least, external driving electronics is necessary with hardware and software support. And of course, last not least, the application and know-how and support in general to manufacture these devices. Here is a piston micromirror array in operation. So you see a sequence of the surface profile measurements in slow motion. Actually, this thing is running, the actual frame rate is 1 kilohertz. It's not yet calibrated, so you see a couple of deviations in here that usually then are calibrated later on. Since we provide these samples as custom evaluation kit, in this case, 256 by 256 matrix, 16 micron pixel pitch, it's not yet holography ready since it's too small and it's too slow. For holography and CGH, we need a higher number of pixels, smaller pixels. We probably run this, or we definitely run this in phase modulation. That is much better than intensity modulation with tilt mirrors that then gives a decrease in available light. The system will be run in analog modulation. Binary modulation would be inferior since pulse width modulation is not possible. So these analog piston types are perfect for holography, but there's no off-the-shelf device available, and we need additional development. These would be key parameters of the final system. The pixel size is 4 by 6. An active area of 16 by 14 millimeter. That's in here, and about 10 megapixels in place in here. So the device itself is, of course, interfaced with LVDS and matrix driving interface. Very complicated structure. It's a preliminary floor plan, and the backplane processing is then provided by XFAB in an XH018 process, whereas MEMS processing is generated by IPMS. Yeah, a couple of other features like small voltage power consumption and precision of 8-bit. Well, first conceptual studies revealed a so-called comb drive actuator. So comb means here the comb in the middle. The actuator is moving up and down between the electrode and the upper electrode, the bottom and upper electrode with the mirror on top. A couple of pros are in here. The actuator gap is very small. There's no pull-in possible. Higher forces are available. Electrostatic forces and much lower crosstalk to the neighboring pixel. But there are challenges. CD is critical. Pattern fidelity is critical, something really new. And probably electrical and pixel defects might become critical in the end. So yeah, there's also other additional challenges like the high aspect ratios, and this individual single hinge in here may end up in tilted mirrors, which of course we do not want. So we improved the design going to a double hinge system that is swinging up and down in a like a parallelogram. Yeah, that's the thing that we are now generating, and it is of course very complex. You can estimate we are dealing with 6 middle layers and 6 sacrificial layers in between. Up to now, we probably have about 500 process steps, including metrology, of course. And you can estimate that the manufacturing time of these systems will be about, yeah, probably up to 1 year if you have only single kind of tool technology in your clean room. That might be very challenging in here. But we started, and we are basically halfway through, to be honest. Using stepper lithography, we generated a couple of features already. You see here a standard Q-type hinge in here that has been patterned with I-line lithography. If you go to the comb drive and you look closer into here, you see that the originally designed straight 90-degree profile is of course not realized using I-line lithography. It is not sufficient, and additionally, you need a higher resolution and optimize pattern fidelity and precision. So CDU is critical, but also overlay. So the placement in here is rather critical. Yeah. Another example, a different hinge type. The hinge is in here, and the mirror may be bent around this small part of the hinge that is flexible. And in the design, it looks like this, rather straight. In I-line lithography, you can already see that the patterns is pretty rounded here. Even if CD shows you that you hit the 400 nanometer, maybe a couple of nanometer left and right, it is not. So uniformity is maybe critical, and also the length of the hinge is rather important to generate the correct, the correct movement in here. So going to deep UV lithography, the world becomes, of course, much easier. Pattern fidelity becomes better. You can enter down to 200 nanometer. That is really nice. And additional features is that you can implement the via in here, so integration becomes much simpler. You can avoid a couple of processing steps in the end. By the way, the asymmetry you see here is, of course, on purpose. It is not an error. Well, deep UV is nice, but as we have an I-line stepper in addition, and we cannot pattern all of our layers, probably something between 25 and 30 litho layers with rather expensive deep UV lithography. We are running in a mix and match mode between these scanner and stepper systems. And what is nice to see is the impact on overlay. So the sequence between different litho steps is rather critical. So in this case, there was a deep UV step afterward aligning on an I-line step, and you see that the overlay budget is pretty nice, of course, due to the deep UV scanner in X and Y. And you can further correct that with pre-runner wafers or forward loop correction. down to the 10 nanometer level. The other way around, aligning on the DPV is, of course, there's a higher error budget in here, and you need to apply these classical forward loop corrections to come in the regime of 10 to 20 nanometer. So with DPV, 10 nanometer stepping precision has been achieved. Alignment accuracy, same direction, and not also there, but also the resolution, of course, becomes much better, as shown in here with the vector graphs. Okay, coming to a last challenge, that is probably, in my case, the most critical part is the chip planarity or topography. So usually when we receive classical wafers from the back end or back end of line of the foundry, wafers look like that. You can see here a high surface inhomogeneity. After the CMOS processing, you can see underlying interconnection pattern or fill factors and so on. And if you want to place high accuracy MEMS mirrors with high planarity, that is basically not possible on this type. So digging into one chip in here, you can see the high thickness variation or topography up to 300 nanometer. Under here, for example, there's the bond pads area that is affecting also the micromirror array in the center of the chip. So applying CMP steps or additional oxide deposition makes it a little bit better, but it's still not sufficient. That's why we use design-specific inverse etching steps before CMP, and that makes the world a little bit better, but it's still not sufficient. So our engineers are clever. In the case of real holography, you see here the comp drive features visualized with AFM that have been covered with an oxide layer. So there's still topography in the oxide. How do we get rid of that? Actually, the standard measurement will reveal a 15% thickness variation, a relative thickness variation across the wafer radius. That is significantly too high. It has been achieved with the standard deposition and the standard CMP step. So if we use more sophisticated steps like additional CMP and depositioning steps of uniform high-density plasma oxide with another bilayer of plasma-enhanced oxide and deposit twice and CMP twice, then we reach a really nice area deviation of only 3.3%. So that's great. That's what we need. That's what we are working for. So in the end, some summary outlook. I've shown you that existing micromirror array technologies are probably the basis for developing future holography SLMs. We are on the way to that. The technology studies as starting point within this EU project are showing high expertise in all the MMA development and manufacturing aspects. Of course, there are remaining process challenges towards the MEMS area. But high resolution, high speed phase modulating MMA may pave the way towards real 3D displays based computer generated holography. So micromirror array technology has probably the potential to push computer generated holograms. Acknowledgements, besides our project partners and consortium, of course, I'd like to thank my team at the Institute, some people from my team, Peter Dürr as project manager, our cleanroom staff, the organizers of the MEMS Manufacturing Conference, and last but not least, our funding authorities. With this, I'd like to thank you for your attention, and I'm open for questions.
Yeah, Christoph, very nice presentation. Thank you for sharing what you guys are working on. Yeah, we can take a few questions. Maybe I'll start. So this consortium for this project that you guys are working on, what can you talk about? What's typically the next step? So as you're developing this technology, you'll get it to obviously closer to commercialization. Is one of these companies going to take this to the next level to commercialize it into a product? Is there going to be some other company? Can you just talk a little bit more about the path to commercialization for what you guys are developing?
Yeah, of course. Since Fraunhofer is a research company, of course, we start at a low technology readiness level. Right. But these EU Horizon projects are exactly designed for this type of this R&D, and but you cannot start them without having application on board. So in that case, of course, it's automotive business where these systems probably will be implemented.
Okay, all right. And I think maybe you mentioned it before, but what are the next? The project goes to December, basically through 2024. So you're still, I guess, somewhat in the first half. But what are the big things this year and then next year on the agenda?
Well, in the end, of course, we have passive devices manufactured without the backplane. That's our part. We hope to have them realized by the end of this year, or the end of or middle of next year. By that time, the CMOS backplane will be available to have the MEMS system placed on top of that. So the end to 2024, the planning is a ready CMOS device with a MEMS device on top that has been characterized by the partners.
Okay, all right. Very good. So, all right, then we can take a few more questions that are coming in here. This is another question from Ricardo Gatti from Stratera. Can you comment on the reverse etching method to achieve thickness roughness control better than a CMP only approach?
Does you mean vertical etching profiles or flatness? Not sure.
It's here reverse. I'm not sure. Reverse etching method to achieve thickness roughness control better.
Reverse, I see. That is addicted to this year, yeah.
Yes, I think so. Yep.
Yeah, the inverse etching is design specific, of course. So we place a specific CMP pattern on top of the topography and etch it back before we start the CMP process. Okay.
All right. Good question, Ricardo. Next question. Are you integrating this holography to MR?
To MR? Well, it's basically part of the partners who will do that.
Okay. All right. And then let's take one more. Let's see. How did you decide that 2 kilohertz operation is required for holography applications?
Well, that comes, of course, from theoretical studies from Serial that otherwise probably the visualization is not possible if a device is too slow. Yeah. Okay. So it's that's the frequency that you need to basically simulate a real object. Okay. Good questions. Yeah. So Christoph, again, excellent talk. The impressive work that you're doing. We'll be watching, and I'm sure we'll be in touch as you guys are continuing to make progress. Encourage everybody to reach out to Christoph and his colleagues. Fraunhofer IPMS does also have a booth with Umbrella, so please connect with Christoph and his colleagues there. Christoph, again, very nice talk. Thank you very much. Thank you. So you will learn more about our clean room capabilities by the talk from Thomas Starbuck tomorrow. The Fab Manager will talk. That's right. Yeah, you guys have another talk that's coming up tomorrow. So looking forward to that too. Thank you, Christoph. Thank you.